So I prepared these slides and I just finished them. Hopefully they're all correct and reasonable. We'll just do whatever we can during the next hour and feel free. It's better to ask questions and to clarify points and interrupt me than to get through everything.
Right. Great.
This is a lot of content. I think the main thing I'm going to be focusing on is this paper and this paper. If you're interested in more details, like it's the first one and the third one. And I'll just be talking about like trying to convey the ideas behind those papers in the simplest possible way. Okay, so you've been studying CTCs during the semester. From the perspective of quantum information, there are two prevailing models. There are Deutschian and post-selected. Have you all studied those?
We've had speakers on it. We've talked with Scott Aronson about that, and
Sean Carroll.
we will be speaking with Lorenzo Maccone next week. So
great.
But we can't hear it enough. So every time a new speaker always brings a different.
Okay, so I'll probably have some kind of different perspective. There is some math, but there's lots of pictures, and so hopefully some kind of clear picture will emerge from that about what's going on. Okay, so to start out, some motivation is that closed timelike curves, or CTCs, they're not ruled out by laws of physics. By the way, I will be using technical terms like closed timelike curves rather than time traveling loops, and so that I don't sound like a crackpot scientist, right? Like these technical terms were invented, and you also see like chronology-violating qubits rather than time-traveling qubits, so that we can publish in journals like Physical Review Letters and be accepted.
Exactly. That's a very important point to make for graduate students.
Right. Yeah. Okay. And these CTCs, they can lead to paradoxes such as the grandfather paradox and the unproved theorem paradox. These are famous examples, and I think Michelle, you have a movie on the grandfather paradox. I've seen it, right?
We do. It's
yes,
a short sci-fi called Steeplechase.
Yeah, I was very impressed with that.
Oh, thanks for watching.
Sure. So the grandfather paradox, I mean, y'all probably talked about it, but for the benefit of my research group, where we don't talk about this in our research group meetings, the grandfather paradox is where you go back in time before you were born and kill your grandfather, right? And so then there's a question of, well, how did you exist in the first place to do that, right? Any model of CTCs will have to attempt to resolve this paradox in some way. And so the Deutschian model and the post-selected CTC model, they both try to resolve it. There's questions, actually, there's papers in the literature whether the Deutschian CTC model practically does that. But we'll just talk about the model and its ramifications rather than talking about these paradoxes. The unproved theorem paradox is where a mathematician reads a theorem in a book and then writes it down, I guess, in another book and sends it into the future. And then, there's a question of like, how did the theorem appear in the first place, right? And so that's another paradox that can arise. What started a lot of this work in quantum information was actually David Deutsch had a very insightful and intriguing paper in 1991, published, I think, in one of the Physical Review journals. And it has lots of interesting discussions, and it set up his model. And then it motivated people to think about these time-traveling information processing devices in a abstract way, using like the language of quantum circuits. Okay, and so as a computer scientist or an information scientist like myself, you might wonder how these fields are affected by them. And you already heard from Scott Aronson about how computation and computational complexity is affected.
Right.
Okay, so the different models, the Deutschian model, that would be the main focus for today. That's the one for which I have the most slides and pictures to describe what's going on. And what happens in this model is that the chronology-violating or time-traveling qubits, they're required to be unchanged before and after you have an interaction with the normal or chronology-respecting qubits. And we'll draw pictures later on to describe this. And he imposes this condition, or he says that nature imposes this condition to avoid paradoxes associated with time travel, like the ones we just mentioned. The post-selected CTC model, this is where actually the famous quantum teleportation protocol comes into play. And what happens is that the chronology-violating qubits are sent back in time by means of the post-selected teleportation protocol. And I'll have some pictures to describe that later on. Okay, so Deutschian CTCs, this is the picture you should have in mind when thinking about them. So there's an incoming state, I'll call it rho. It's described as a matrix that's called a density matrix that has certain conditions. We'll use the fact later on that it generalizes a probability distribution. And so this is the normal qubits, and the time-traveling qubits will denote by sigma, and that is also described by a density matrix. So the idea is that time is flowing from left to right. The normal qubits come in. They haven't interacted with the time-traveling qubits prior to this point, and so the state of the system S and the CTC system C mathematically is described as what's called a tensor product state, meaning that they're independent of each other before the interaction occurs. We'll later see how that's actually, one can debate this, whether that's the case based on what happens with the model. So then at this point in time, they're allowed to interact according to a unitary. So in quantum mechanics, the standard form of evolution is a unitary evolution. So this is some unitary matrix, which means that it's easily invertible. And then the time-traveling qubits, they go back in time. They're sent through what's also, this is a technical term, future mouth of a wormhole. And this part is called early mouth of a wormhole. Okay, and so then these go back and then these go on. And actually, so what I'm doing here,
just for the students out there, the tensor product is to give a notion of being, you're going along with your matrix row and you're on light cone, and the tensor product is a way to correlate yourself, your own experience with the environment in some sense, right? If you had to describe it at a high level phenomenologically for
yeah,
people.
it's like the tensor product means that they're independent and then they're brought together, and then you use the tensor product to describe the state of such a scenario. Okay. And then I'm using this notation omega to refer to the joint state after the unitary interaction. So after the unitary interaction, they can become correlated, and you have to describe their state jointly. But what happens is that the system goes on and the time-traveling qubits go back in time. And so you impose this thing called partial trace to describe the state of the normal qubits as they go on. Okay, so mathematically, what Deutsch imposes is what's called a fixed point equation. So what he says is that the local state here has to be the same as the local state here in order to avoid these time-traveling paradoxes, right? And so you probably heard Scott Aronson say in his talk, like his resolution of the grandfather paradox is that with probability 1/2, you kill your grandfather, and you didn't exist, and thus with the complementary probability, also 1/2, you didn't kill your grandfather, and so then you exist to go and kill your grandfather. I guess, you know, I'm now a father, and so maybe this is a bad joke to make, but as a grandfather, I would only be so honored if my grandson would come and kill me someday. Just kidding, just kidding.
Time travel joke.
I hope that he doesn't hear that like right now. Okay, so the fixed point equation is this. What this is saying is that after you discard the state of the system of the state omega, after you discard the system S, you're left with a density matrix that describes this system here, okay? And if you follow quantum mechanics, we said the initial state was a tensor product state. That's this state right here. Then there's a unitary evolution. After the unitary evolution, you describe the resulting state by this. This is also a matrix. And then there's this operation called partial trace, which leads to the output state. So Deutsch says that the state here has to be equal to the state here. But then if you abstract things a bit, you can think that in standard quantum mechanics, we use the language of quantum channels. And so this process realizes a function of the density matrix sigma that depends on the input state rho and depends on the unitary u. And so what's weird about this is that sigma, the state that nature finds, depends on rho, depends on this input state, even though they have not interacted in the past, okay? Yeah. And so that's a funny thing. And this right here leads to what's called nonlinearity and a distinction with standard quantum mechanics, okay? And so this is the equation that we'll be playing around with to make funny things happen in, let's call it Deutschian quantum mechanics, okay? So that's the model. And in future diagrams, we'll be using this abbreviation rather than writing loops everywhere, because there'll be a lot of loops. We'll envision this as the early mouth of a wormhole, and then, you know, it's going through, interacts, then it goes through the future mouth of the wormhole, and then this is identified with this, okay? So we use that shorthand notation for our diagrams. Okay, so indeed, you know, this resolves paradoxes through this self-consistency fixed point equation. Although, as we said, that you can find papers debating that point in the literature. The price to pay for this resolving the paradoxes is that, as we said, you eliminate this cherished principle of linearity of quantum mechanics. And so there are severe dramatic consequences of this, but this is also debated, okay? And indeed, as you know, there are debates on the actual power computationally and information processing wise. I don't know if Scott Aronson addressed that in his talk, but at least in his book, I think he has a chapter where he calls it the CTC wars or something like that, where these debates are discussed. Okay, and so I will take a certain position and just argue the perspective that we had in our research papers, where we argued that they can in fact allow for distinguishing what's called non-orthogonal states and also copying them. And these are, you know, powers in violation of the basic principles. And as a little break before we move on, I'll show you, as it goes with social media, you can see this is a short summary of the debate. So this is Graham Smith, who's a co-author of one of the teams adopting the other side, talking about his paper, saying
Are you
that
trolling, Mr. Smith? I see on the right side some aggressive comments.
Yeah, this is all just joking around. So, but he, you know, he was responding to some tweet, and he said, "We wrote our paper to beg people to stop being stupid about nonlinear models of quantum mechanics. So, that means that here, everything that I'm saying today, Graham considers stupid. And then he said, it did not work. And then I wrote about our paper. The following stupid paper was published in PR after your stupid paper appeared. And we dedicated a paragraph near the end to discuss your paper and its stupidity. And, I violated a basic rule of social media. If you're kidding, you're supposed to put a smiley face. I didn't do that. And so he thought I was angry, but I was not. And so I said, okay, just kidding, don't worry. But pleased that this, annoyed you. Okay, so.
I have some issues with getting emojis right too. I'm sympathetic.
Good. Okay, so now for the rest of the talk, I'll just adopt this position, and we can discuss. I don't know if there's going to be time, but we'll see how it goes. Okay, so I want to tell you how you can distinguish non-orthogonal states, and to give you a background on this, because you said people in the room, it's engineers and architects, and they might not have seen all this math. So we said that states are described by matrices, and they're said to be orthogonal if when you multiply the matrices, you get the all zero matrix, so a matrix of just all zero entries. The meaning of that is that if they're orthogonal, then you can actually perfectly distinguish the states, right? So, classically, so in the classical world, like all states are distinguishable. If I flip the light on or flip the light off, I can tell the difference, and that would correspond to orthogonal quantum states. But in quantum mechanics, okay, so I'm just elaborating on this point. So if a system is prepared in either of these orthogonal states, then you can perform what's called a quantum measurement that will never make a mistake in identifying the unknown state. Okay. On the other hand, in quantum mechanics, you can have non-orthogonal states. And in that case, they're not distinguishable by a measurement. That's in standard quantum mechanics. So what we're going to show is how Deutschian CTCs can violate this. And this is what I'm going to call, and I really want to hear Seth's laugh. So it's called the devilish Deutschian distinguishing device. I want to hear the mad scientist laugh.
Yeah. Did you hear
it? Couldn't quite hear over Zoom. All right. So, but the laugh if you're in Seth's class. Okay. So we're going to talk about this device, this devilish distinguishing device. And we're going to show that the simplest case is there are two states to distinguish. One state we'll call zero. It corresponds to this 2x2 matrix. Another state we'll call minus, and it corresponds to this 2x2 matrix. And if you multiply these matrices, you're not going to get all zeros. Okay, so these are the ones they're non-orthogonal, and we're going to show how to distinguish them. We're going to argue in kind of a rough way and not with detailed math. So this circuit is one that does the job. So remember the general model, we have the incoming state, the CTC, and then some unitary, right? And then the CTC. In this case, the incoming state is a qubit, the CTC is a qubit. This is a logic gate called swap. It just physically swaps the systems, okay? And then this is something a little more exotic. It's called controlled Hadamard, okay? And I'm going to explain what that means in the next slide. Okay, so this symbol denotes a swap gate, as we said, and this one is controlled Hadamard. What does the controlled Hadamard do? It has two inputs. If this input qubit on the top, let's call control qubit, if it's zero, it actually doesn't do anything, okay? Whereas if the control qubit is one, it applies the Hadamard. And I didn't write in the slide, but the Hadamard takes the minus state that we had on the previous slide to the one state, okay? And then that's going to be the underlying part of the trick that does the distinguishing. So how does this device work? Well, if you're going to analyze a time-traveling circuit, the best way to do so is to trace its evolution backwards in time, okay? So that's what we're going to do. So we're going to suppose that the output state here is 0, and then we're going to kind of like propagate this through and then see what happens, okay? So this is 0, and the controlled Hadamard has the property where if the control qubit after or before is 0, then that means that, like, if the control qubit after is 0, that means the control qubit before is also 0, okay? So it has that property. And then we're going to so if the control qubit before the controlled Hadamard is 0, as we said before, that means the controlled Hadamard does not act. So it's like it's not there, okay? So now we have this picture, and now this picture is much simpler. This we said is the swap. So it does that. It'll swap this here, okay? And then the state of the CTC at the beginning is the 0 state. And then according to Deutsch's equation, the state of the CTC here has to be the same as the state of the CTC here, right? And so then you get 0 here also, right? Now we're going to propagate this back in time again through the swap. So this gets swapped into 0. And so what this does, what we did is a rough proof that a self-consistent solution for this circuit and Deutsch's equation is where the state of the normal qubit is 0 and the state of the time-traveling qubit is 0 also, okay? So what this circuit will do, if we did this analysis in a rough way, right? So what happens is the 0 comes in, and then because this is a self-consistent solution, you can actually also prove that it's the unique solution. We didn't do that. But what will happen is the 0 comes in, the CTC gets prepared in this 0 state, and then the rest of the circuit acts, and you'll get 0 at the output and 0 here. Okay, so the circuit will take 0 to 0. All right. Any questions about that? Because that was like a conceptual part of this, where it was kind of like a graphical proof and solution of Deutsch's equation.
I don't see hands raised, so.
Can I just,
Thank you.
I'm slightly concerned, given the weird nonlinearities and stuff, whether it's okay to run the thing backwards in time and say that's what happens.
So this was meant to give some kind of intuition for what's going on.
Yeah.
When you run through the math, it does lead to the correct conclusion.
Right, I believe that this is a fixed point of the tracing out of the second part of the CTC and Deutsch's equation. I believe you would.
Yeah. Okay. All right. So now we're going to do the same for now we're going to suppose the output is 1. Why that output is orthogonal to 0, right? So if you have 0 or 1 at the output, then you can distinguish those states perfectly. Okay. So now we're going to do the same funny analysis that ends up being consistent with the correct mathematical solution. So let's go. So now the output state is 1. This is a typo, my apologies. This is meant to be 1. So
Can't
actually,
screw it up, Mark, not in a talk like this.
yeah, let me just correct it real, because I'm afraid it's going to cause a problem. Okay, so it's corrected. It's corrected. Okay. Okay, so if the output is 1, then the controlled Hadamard has the property that's similar to what we said before. If the output is 1, the input is also 1. So in this case, the controlled Hadamard will act. You can see the typo persists. Sorry, so I won't continue to correct it. So this control qubit is 1. This thing goes backwards through the swap. It's 1. For self-consistency, the state of the CTC should be the same as the state of the CTC here. We're going to do that. And as we said, Hadamard takes minus to 1. Hadamard is actually self-inverse, so it will take 1 to the minus state. okay? And then this gets swapped, now we're going backwards, this gets swapped, and the input state is minus. So this is like a rough proof that a self-consistent solution in this case is when the input is minus, the state of the CTC is 1, okay? And so now this is quite dramatic, right? Because we said in standard quantum mechanics, you cannot distinguish non-orthogonal states. And so what this circuit does is it'll take minus at the input to 1 at the output. It'll take 0 at the input to 0 at the output. And then this is perfectly distinguishable from this, okay? So that is quite strange. And, you know, that's actually what motivated Charlie Bennett and Graham Smith to write their paper, because they thought this was so strange. And in the language of Graham Smith's tweet, stupid. Okay. And, you know, and so the claim is that it violates this cherished uncertainty principle. And so that's quite bizarre. Okay. So now you might wonder what other devilish things can we do that will violate these laws of quantum mechanics, right? So something that's even more devilish is we had a CTC in our example that we studied so far. We had a CTC consisting of 1 qubit, and we showed that it can distinguish 2 non-orthogonal states. That can actually be generalized where a CTC with a single qubit can be used to distinguish 2 arbitrary non-orthogonal states, okay? But we can do something much more dramatic. If we go, so a qubit is what's called a 2-dimensional state. If you have a larger CTC system that's d-dimensional, so it's somehow more powerful and I guess bigger in this mathematical sense, that can be used to distinguish d non-orthogonal states, right? So, for example, if I had a CTC system consisting of 10 qubits, the dimension of it would be 2 to the 10, and it could be used to distinguish 2 to the 10 non-orthogonal states, right? And so that's quite dramatic. And if you want to see, that gets a lot more hairy mathematically. If you've studied linear algebra, this was a fantastic application of what's called the Gram-Schmidt orthogonalization procedure, which is something you learn in an undergraduate linear algebra course. And so I was really blown. It was Todd Runn who proved that. I was really impressed when he did that using that basic tool. Okay, so that's even more dramatic. But then we can ask ourselves, is it possible to be even more devilish, right? And the answer is yes. And so that's quite exciting. Deutschian CTCs furthermore allow for cloning quantum states. There's a principle of quantum mechanics called the no cloning principle. It says that you cannot copy arbitrary quantum states unless they're classical ordinary states, right? So we copy things all the time, right? When we you know, write notes down on a piece of paper when the professor's teaching, right? You're copying the information. What you're copying is classical information, but that's not possible to do for general quantum states. Okay, so that's something called the no cloning principle of quantum mechanics. This is actually stronger than distinguishing non-orthogonal states and is not allowed in ordinary quantum mechanics. So mathematically, what does a cloner do? It's a device that takes an input state and produces 2 independent copies of it, right? And if you have such a device that can do that, you can repeat it and generate an arbitrary number of copies, okay? And so the next devilish device will show how to do this, and we'll build it up in stages, okay? So this is now, previously we had the distinguishing device. This is a devilish Deutschian duplicating device, okay? So we're gonna start simple.
It breaks all of crypto.
Yes.
For sure.
Yeah. So what we're going to do is start simple and consider this circuit. Okay, so what is this doing? For the purpose of thinking about this, you can think that each line represents a single qubit, and the CTC now consists of 3 qubits, right? So this this one will go through this wormhole and go back to here. This qubit will go through this wormhole, go back to here. This qubit will go through this one and go back to here. I didn't draw the loops, otherwise it would be a nightmare, like studying the diagram, right? Okay, so now what are we picking the unitary interaction to do? We're doing what's called a cyclic shift. We're taking this qubit, we're swapping it here, taking this one, moving it here, this one moving it here, and this one moving it out, okay? And what happens in this case, if you have an input state, a self-consistent solution is it's everywhere. The state is everywhere, right? So a self-consistent solution is that rho goes to rho, right? Rho is here, it appears here, this is rho, boom, 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 here's rho, goes back, this is rho, goes back, and then goes out, okay? So rho's everywhere. And it's also, you can also prove this is like, so that was an argument that it's a self-consistent solution. It's also, you can prove this is the unique solution for this particular setup, okay? So when you look at this, you might think, oh, great, we have copies of, we've made copies of rho, we've cloned, you know, rho is here, rho is here, rho is here, rho is here. But it's actually not useful because once these wormholes close, these copies are gone, and there's only one surviving copy of rho, of the original state. And so it's like it didn't accomplish anything useful at this future time, okay? So that's what this is saying. In the circuit, copies of rho are inside the CTC, but they're not available at the output, okay? So what we have to do is figure out how can we modify the circuit such that we can make the copies available at the output. And that's what we'll do for the next few slides. Okay.
So just the notion of having it being copied without it being sort of a time-based circuit makes me think of some quantum mechanical equivalent of p-space or something. It's like, it's
I see. So the complexity class
laying down one distributed memory, but it's sort of taking up the space on this mathematical formalism, filling it all up. So yeah, it's
maybe there's a way to relate this specific circuit to a computational device that has p-space complexity.
right.
And I do remember a while ago reading the proof of Watrous and Aronson, and they might be doing something like this, but it's been a long time, and so
Yeah, it's worth taking a look. I'll follow up with you on that.
yeah. Okay. Good. So the first scenario we're going to consider is that rho is a classical state. So what does that mean mathematically? That rho only has entries along the diagonal of the matrix, okay? And that's quite a special case. And it corresponds to those entries along the diagonal forming a probability distribution, okay? For a classical state, you can interact with it without causing a disturbance, right? So just to go back to this previous slide, if we have a general quantum state and we do some interaction here to try to like read these out, then you'll cause a disturbance to the state that could throw off the fixed point equation such that these copies of rho are no longer the solution. They could just go berserk, right? But in the classical case, you can interact with these states without causing a disturbance. Okay, so this no disturbance principle is something we can invoke in making the construction. So the classical case is unlike the general quantum case. So in the classical case, you can do this broadcasting circuit, okay? So if you studied quantum computation, this is a gate called controlled NOT, and it's one of the standard gates used in quantum computers. And people at IBM, MIT, and Cornell who are building quantum computers, one of the gates they have to make is this gate. So in our context, we don't need to go into so many details of it, but it has this broadcasting property. So if rho is an incoming classical state, and we do the C naught, it'll make a joint state called omega that will have correlations between systems 1 and 2, such that if you trace out, if you discard the first system, the reduced state of the second system is rho. And if you discard the second system, the state of the first system is also rho, okay? So this is what's called broadcasting rho, such that like, if I had a receiver here and a receiver here, they would both locally see the state rho, even though the global state is not a tensor product of rho and rho. It's actually some correlated state. But this broadcasting property suffices for our purposes in making a cloner of classical states, okay? So this is the duplicating, this is what we started with before. So we're gonna modify it to include these broadcasts, okay? So that's gonna be these, right? So, and as we said, for classical states, these broadcasting portions do not cause any disturbance. And so the self-consistent solution and unique one of Deutsch's equation is still rho these 3 copies of rho for Deutsch's equation. And then, so you can read these out, and the broadcasting property ensures that when you discard, when the CTC is gone, you still have 4 copies of rho, okay? So this is a construction that copies classical states. And this is actually not allowed in classical probability theory. It's a big no-no for that also, okay? If in probability theory, you model evolutions as what's called stochastic matrices, okay? So this is our second step. The first step was to do the shift. The second step was to think about just the classical case and the broadcasting. And now we're going to do a third step, which will handle the general case. And so I'll tell you, like, from a personal perspective, I was in Todd Brun's office. He told me about this construction. And then a week later, I was in Andreas Winzer's office in Barcelona in 2013. I said, Andreas, we have this device. We really want to clone Palm states. And then he looked at it, he said, why don't you just do an informationally complete measurement? I was like, oh, of course. All right. Brilliant. And so then I went back and did some calculations like, okay, yes, indeed it works. Perfect. So let's talk about that final step, how to make it work for general quantum states. For that, I have to tell you about this notion of informationally complete measurements. So in standard quantum mechanics, you learn about a quantum state in experiments, you prepare multiple copies of it, okay? And then you can perform the same measurements on different copies, okay? And you can use the outcomes of the measurements to make an estimate of the state rho. So, as we said, this state is described by a matrix with some number of entries. For a qubit, it's just a 2x2 matrix. So you just have to learn these 4 numbers for a qubit, right? If you had just a single copy of the state, you would not be able to fully learn the state. You would learn basically nothing about it by performing a single measurement. But if you have multiple copies, you can do this procedure. It's called tomography because it's like you're looking at the state from different perspectives. And this is routinely performed in the lab, okay? But the key to it is that you need multiple copies of the state. Okay, and when the measurement has this property of being informationally complete, it means that from the measurement outcomes, there's what's called linear invertible map that transforms the probability distribution for the measurement outcomes to the density matrix. Okay. And so you can, like, from the measurement outcomes, you can go to rho, and then from rho, you can calculate the probability distribution for the measurement. Okay. And I have a little bit of math to describe what this is, because I don't know, I guess I think in these terms. So in quantum mechanics, this is one of the postulates. A measurement is described by a set of, say, like some number of matrices that have this property of being positive semi-definite and sum to the identity. This is analogous to how a probability distribution is a list of numbers, each of which is positive and sums to 1. Okay. And the probability for getting outcome X is given by this Born rule. Okay. So this is one of the most important things in quantum mechanics. It's called the Born rule. It's how we calculate anything in any experiment, in any quantum mechanical experiment, and make predictions. Okay. So for a given measurement, you can define a probability vector that corresponds to the probability of getting each of the measurement outcomes. For an informationally complete measurement, there's this linear map that will take P to rho, and it'll go from rho back to P. Okay. And so that's going to be key to the final step of the construction. So this is somehow the most complex part of the construction, but it leads to the ability to clone general quantum states. Okay. And so the only modification to the previous circuit is right here at the beginning, you do the information complete measurement. That's it. Okay. So you do this, you then get a classical state, it's like this classical probability distribution. You use this classical cloner that we had previously, and then you get multiple independent copies of the classical state rho m, right? And then from those, you can make as many of these as you want if you have a CTC system that's large enough. And then from these, you can learn about what the state rho is. Okay, so that's the full construction. So it's like you did the disturbance before the CTC comes into play. You then have a classical state, and then you do this full thing. And then from these independent copies, you can figure out what rho is. Okay. And so it's kind of like a device that reduces the space of all density matrices to like a single deterministic, each of them is like a deterministic point that can be perfectly distinguished, right? And so that's a way of thinking about what this is doing. Okay, so this is just summarizing what we said. At the end, you get these multiple copies of the classical state rho m, the measured version of rho. From these, you can form an estimate of the probability vector, and then you do this linear transformation on that estimate, and then you get an estimate of rho. And what's key to this, you can prepare as many copies of rho as desired. And what's called the law of large numbers from probability theory guarantees that this estimate can be made arbitrarily close to rho. Okay. So that's the full cloning construction. Any questions on that? Because we have about 10 minutes. I can basically show you one more thing and summarize. Okay, but if there's questions about what we just discussed, this is the cloning device.
Mm-hmm. Yeah, I think.
But that doesn't clone rho yet. It's just doing this cloning rho m, right? You still have another step for. You still have another step.
I didn't quite hear. I think what I heard is there's this rho m, and then
But you still have another step for cloning rho, right? You haven't gotten around to cloning rho yet.
Yeah. So the point is that from these rho m's, so yeah, I didn't say that. From the rho m's, you can form this estimate of rho hat, and then using that estimate, you can prepare as many copies of rho as you want. This is, so if people, I don't know if people are interested in like future research on CTCs. This is by no means efficient, right? So like if rho is a qubit, if it's like a state of 2 qubits, there's going to
That was
be,
actually my question. Yeah, it's how scalable is the system, and
yeah, because now we're
could it
thinking
be
like
adapted for large?
near-term quantum computers, right? Like,
Right.
like can this be done in the near term? It's a good question. So if rho is 10 qubits, then it's described by roughly 2 to the 10 numbers, right? And it's too many. And so this procedure is not efficient. So a very interesting research question is, how do you make this efficient? How do you make it computationally efficient, right? This part is computationally efficient. This part is computationally efficient. This is also, but then this last part where you take this list of 2 to the 10 numbers and then generate a state from them, that's completely inefficient, right? But this was more about the information theory and not necessarily about the complexity theory. So, but as far as I'm aware, no one's followed up on that in the future or the present or the past. So sorry, there was another traveling joke.
A good joke. No, so
Right.
given that TCTCs and CTCs are information theoretically the same, is there, how does this, does it influence the boundary between PP and P space in some way? Has this been written about?
So to show those, I don't know if anyone has related the ability to clone to complexity. But yeah, I guess the basic answer to your question is I don't know. I don't know how this influences the classes PP and P space. So P space is what you can achieve with Deutschian CTCs, and then Seth and his group of co-authors proved that these PCTCs, which are this class PP. So
right. You and Todd showed that you can use these projective closed timelike curves as well to do cloning, right? Didn't you guys have paper?
They cannot be used for cloning.
They can't be used for cloning. Or you had a
yeah.
paper with the consequence was that it was negative, that they can't be used for
That's
cloning.
right. So they can be used to distinguish linearly independent states. So they can be used to distinguish non-orthogonal states, but the power is limited. So, all right, I want to show you the next thing, and then that will basically be it. So the whole discussion today will just be about Deutschian CTCs, and that's fine. Actually, but if no one knocks on the door, then I can continue past 3:30 if desired. Okay, so this is what we said. Okay, now there's a question of how can we simulate a Deutschian CTC in the lab? And you see there's a typo here. Somehow 2 days ago, and the H has become, it kind of went out on my keyboard. So I have to really hit it hard to make it appear. And I was in a rush at the end and I didn't notice that. Okay, so how can you simulate a Deutschian CTC in the lab? Recall this basic model. What's happening here is that the CTC output is fed into the CTC input. And so there's a question of how can we simulate this in standard quantum mechanics? Okay. So what we're going to do is we're going to unravel this. So this is what we're calling the Deutschian unraveling. So the point is that you'll need multiple copies of rho of the input state, okay? And then you'll prepare the CTC system in some arbitrary state. I'm calling that tau. You let them interact according to a unitary, and then you feed the CTC back in to the input for the next one. And that's like what we were doing where you're feeding it back in. But the previous diagram, it's like it happens in one shot, right? But here we're doing it repeatedly. So you do it once, then you do it again, okay? And then in some cases, depending on the unitary U in the state row, after you iterate this sufficiently many times, the state of the CTC will converge to the fixed points of the Deutschian fixed point equation. Okay. And so, but this is, time is flowing left to right. In this diagram, there's nothing going back. Okay. So the point is that you just repeatedly do this some number of times. And you might have to do it a large number of times. So it's not going to lead to an efficient simulation, right? But in some cases, it will converge fast. Okay. So I had this thing about in some cases, there's a little mathematical thing where you have to be careful. You actually need to do, to make it work in general, you need to do this as a controlled unitary. And you pick this state gamma to be what's called probabilistic mixture of 0 and 1. And then this will always converge to the fixed point. So I had a paper with Todd about this called the simulations of closed timelike curves, something like that. And this I think is very interesting. As far as I'm aware, no experimentalist has done this in their lab. But of course, nowadays we have quantum computers. So I haven't worked on this topic since around 2016, I think. And then quantum computers, that's when they started coming online, right? So nowadays you could actually do this on an existing quantum computer. So it'd be nice to see this kind of experimental simulation. And the caveat having to do with complexity theory is that the convergence to the fixed point might be slow, right? And so by doing this simulation, we don't get an efficient simulation. But in principle, it's something that could be done. And I think it's an interesting way to connect standard quantum mechanics with Deutschian quantum mechanics, right? And then like in this simulation, to make it work, you see there's this kind of copying of rho going on, right? And so that's kind of what's going on in the actual Deutschian setup, right? Like mathematically, this is equivalent to this, where after some number of iterations, this final system is what goes out. And then this is the final state of the CTC that has converged, okay? Yeah, and then I had a summer student when I was back at—
Could I interrupt for a second? So I was just wondering about, given that you were talking about experimental design, like, is there any kind of at a high level practical heuristics you could give to the design of experiments, the difference in between design of experiments between that entail post-selected closed timelike curves versus the TCTCs? I know you just explained a different experiment, but just sort of overall.
So when you say T, do you mean D for Deutschian?
I was thinking of your paper, the work you did with, I think it was Todd.
It was with Todd, yeah. So that's actually a third model that I've been avoiding during this talk, because we showed that it's pretty much equivalent to the post-selected model, and so
let's say between D and P, if you were talking to an experimentalist who was really out there.
I don't know if okay, so is there something between Deutschian and that like interpolates between them? I don't know the answer to that. That's an interesting question.
I have no idea.
I never get answers from you people, from you guys. I don't know why.
But if you want to simulate Deutschian CTCs, this is a blueprint of what you do, right? You would do these quantum logic gates like this, and you need a circuit to prepare multiple copies of rho. For PTCs, I can show later how you would simulate that. You do it via this post-selected teleportation, and you only keep the outcomes where it's kind of like you imagine you get lucky, where you always get a certain outcome from the teleportation measurement. And then for TCTCs, I haven't looked at them in a long time, and so I don't quite remember the details of them. But the thing I do remember is that we proved this information theoretic equivalence to PCTCs, and so I kind of just ended up discarding them. Yeah.
Yeah, that
And
makes
I
sense.
actually, when I was preparing this talk, I looked up the author of TCTCs. His name's John Mark Allen. He's now moved on with his life and he's working on self-driving cars in the UK. So maybe in the future they'll incorporate a TCTC device in them.
A little more
Um,
practical.
Yeah. Okay, so what we did do with the summer student who's now doing a PhD at Urbana-Champaign, we actually used the simulation and the distinguishing device that I showed earlier to construct practical state discrimination schemes. They can be used for this task of interest in practice. And so, and then we could quantify their performance. So I'm just mentioning that. Okay. So we're at 3:33. I can continue until there's a knock. And so we can discuss post-selected CTCs, unless you want to.
Yeah, we also have time constraints, so maybe
Okay,
another 5 minutes would be okay.
5 minutes. Okay, it's actually quite short.
Okay, great.
Also, Lorenzo's going to be here next week, and he will also tell us about PCTCs. So
Great, that's great. Yeah. Okay, so in the PCTC model, the diagram looks similar to the Deutschian model, except I've made this little adjustment with how we're depicting the CTC, because it corresponds with notation used in quantum circuit language. And so, yeah, the mathematical specification is very different. So my understanding of the history of this is that Jim Hartle, who's now passed away, he was doing something like this in I guess, quantum field theory and like a path integral formulation. And then Charlie Bennett and Ben Schumacher, these pioneers in quantum information, they came up with this model, but I think they were very concerned about their reputation as scientists, and so they published nothing. And then Seth.
Jim's paper was actually about, it's also it was about universes with both initial and final boundary conditions.
I see. Yeah.
So about the relationship between path integrals and how do you represent this quantum mechanically? Yeah.
Yeah. And so then Seth and his team around 2010, they actually were confident to publish something about the model.
We also didn't know about Charlie, and because they didn't publish it, so we didn't know about
They
Charlie.
didn't publish it, exactly. Yeah.
I guess the question is the path integral where they weren't classical paths, and this is some kind of analytic continuation with
I think the assumption was classical paths, not like superpositions of paths. But Seth does have a paper where he showed the precise mathematical connection between post-selected CTCs and the path integral formulation of Jim Hartle. And that's I remember reading that when I was a postdoc in 2011 and finding that very interesting and fascinating. Okay, so how do post-selected CTCs work? Well, you can study them in terms of a diagram that looks like the diagram for quantum teleportation, right? So there's the initial state of the normal qubits, and then you actually have two systems. This D is like a system of the same size, of the same number of qubits as the C system, and it's prepared in what's called the maximally entangled state. It's the standard resource state used for quantum teleportation. So then the system S and the CTC system are allowed to interact according to the unitary U. And then these two systems are measured according to what's called the Bell measurement. And that's the standard measurement used in quantum teleportation. However, the key difference is that we imagine in post-selected CTCs, it's like you get lucky every time, and only one measurement outcome occurs, okay? And the way that you could simulate this experimentally, it'll take a long time, but you do this circuit, and you do this Bell measurement, and then you write down all the data that you get from the experiments, and you could do measurements on this output state omega. But then you only keep the outcomes, you only keep the data where a certain measurement outcome occurs from this Bell measurement. Okay, so it's like you're discarding most of the data that occurs in the experiment. Okay. And these are just descriptions of what we already said. Phi is the maximum entangled state, measurements of Bell measurement. And then, as we say, this model postulates that a certain measurement outcome occurs with certainty. If you want to write it down mathematically, this is the mathematical language. So it looks, some aspects are similar to what we had previously. You have the initial state rho, its in tensor product with this maximum entangled state. The system S and C evolve according to this unitary evolution. And then this is now the projection onto the system C and D corresponding to the maximum entangled state, and then this trace over C and D. Okay, and this, and then I write proportional to, and this is actually the key that makes the model nonlinear, right? So we use this term nonlinear previously, and that's what leads to extra power. Seth actually has a paper, I think, with someone named Abrams. I don't know if Seth is a co-author, where they show that any nonlinearity can lead to enhanced processing power in quantum mechanics. And so due to this proportional part, this output state has to be a state. So it means you have to divide by what's called the trace of this operator. And then that induces a nonlinearity, okay? So this model is equivalent to, if you want a simpler way to write what this omega is, it's a state that's proportional to this matrix, where this one is described by a partial trace over U. And that's discussed in Seth's paper. So the powers, this is what I'm just going to state briefly, and then we're done. So you can distinguish non-orthogonal states, but only those that are linearly independent. So you cannot distinguish arbitrary non-orthogonal states. But by doing so, you still violate the uncertainty principle. But there's also a limit, because you only have this thing about linearly independent, you cannot clone in this model, okay? And then, as we said before, there's implications for computational complexity theory, and that's discussed in Seth's paper. So just to summarize, what did we say? We basically did three things, if I remember. We discussed a device that can distinguish non-orthogonal states. We discussed a device that can clone arbitrary quantum states. And then we also discussed simulations. We discussed simulations. Post-selected CTCs are much less powerful. One can debate whether these can even exist in nature. I have a personal opinion that Deutschian CTCs, I don't think they can exist. But it's not something we can experimentally prove. And there's just so many, there's other kinds of problems with them. They lead to too much power, in my opinion. Post-selected CTCs, there's more of a chance for them, and Seth can certainly comment much more on this. He has a paper with John Preskill, where there's a certain model of black hole evaporation, where they argue that this post-selected CTC and post-selected teleportation could play a role in describing what's going on there. The other thing I want to mention, there's recent work with a student here at Cornell. You could reassess all of the fields of what's called quantum Shannon theory. What are the fundamental limits of communication? You could say, okay, what if we augment the sender or the receiver with a time travel machine? Can they have higher rates of communication? What we proved recently with Kai Yuan is that in the post-selected model, there's actually fundamental limits. And we actually found a formula for the capacity that, in some sense, is a mathematical modification of Shannon's formula. And so I was very pleased with that. We published it in a special issue of a journal dedicated to Alexander Halevo's 80th birthday, who's a pioneer in quantum information theory and still quite active with research. So that's the final thing I'm saying. Thank you for the opportunity. I enjoyed the
Great, thank you.
discussion
Thank you so
and,
much for coming, talking to the class. It's really a real treat to have you here and to talk more about these very obscure subjects that people think
Yeah.
is stupid, as you say.